Have you ever looked up at the night sky and wondered why planets are all lined up in the same flat plane? Well, you're not alone. This question has intrigued scientists for centuries. In today's video, we're diving deep into the cosmos to uncover the fascinating science behind this celestial alignment. Why do all the planets orbit in the same plane? Stick around as we unravel the mysteries of planetary orbits and explore the incredible forces at play. Trust me, by the end of this video, you'll see our solar system in a whole new light. Let's get started. The first concept we need to explore is the formation of the solar system itself. Picture this: about 6 billion years ago, our solar system began as a giant cloud of gas and dust. This cloud, known as a solar nebula, started to collapse under its own gravity. As it did, the materials in the center began to heat up, forming the sun. But what happened to the rest of the cloud? Thanks to the force of gravity, the remaining dust and gas started to flatten into a spinning disk known as the Protoplanetary disk. This is where the magic happens. In this disk, particles of dust and gas began to collide and stick together, forming larger and larger clumps. Over time, these clumps grew into planetesimals and eventually into the planets we know today. The crucial thing to understand here is that the protoplanetary disk was flat and rotating. Gravity played a key role in keeping this disk stable and maintaining its shape. As the planets formed within this disk, they inherited its flat, rotating characteristics. This is why all the planets orbit in roughly the same plane, known as the ecliptic plane. Essentially, they are tracing the path of that ancient, flattened disk where they were born. So when you look up at the night sky and see the planets aligned, you're actually seeing the remnants of a process that began billions of years ago, guided by the fundamental force of gravity. The second concept involves understanding the physics behind the conservation of angular momentum and how it led to the formation of a flat, rotating disk of gas and dust. Angular momentum is a property of any rotating object, and in our case, it applies to the spinning solar nebula. Simply put, angular momentum is the tendency of an object to continue rotating unless acted upon by an external force. When the solar nebula began to collapse under its own gravity, its rotation sped up much like a figure skater pulling in their arms during a spin. This increase in rotational speed helped to flatten the nebula into a disk. Imagine a pizza dough being spun in the air. It starts off as a ball and gradually flattens out into a disk due to the spinning motion. In the same way, the solar nebula's rotation caused it to spread outwards and form a thin, flat disk. This disk was primarily composed of gas and dust, all rotating in the same direction. The conservation of angular momentum ensured that this rotation was maintained as the solar system continued to evolve. The particles within this disk stuck together through collisions, gradually forming larger bodies like planetesimals and eventually planets. Because the entire disk was rotating uniformly, these newly formed planets inherited the same rotational path, leading to their orbits aligning in the same plane. So, the next time you gaze at the night sky, remember that the alignment of the planets is a beautiful consequence of angular momentum, a fundamental principle of physics that has governed the motion of objects in our universe for billions of years. The third concept involves delving into the process of planetesimal formation within the protoplanetary disk and how these planetesimals eventually formed planets. As the protoplanetary disk spun and flattened, the fine particles of dust and gas within it began to collide and stick together due to electrostatic forces. These collisions, while initially gentle, were sufficient to cause small clumps of matter to adhere to one another, forming larger and larger aggregates. Over time, these aggregates formed planetesimals, which are essentially the building blocks of planets. Picture these planetesimals as small, rocky bodies, ranging from a few meters to several kilometers in diameter. As these planetesimals orbited the young sun, they continued to collide and merge, driven by gravitational attraction. With each collision, planetesimals grew larger and their gravitational pull became stronger, allowing them to attract even more material. This process, known as accretion, led to the gradual growth of these bodies into protoplanets. The environment within the protoplanetary disk was dynamic and sometimes chaotic. Some planetesimals were shattered in collisions, while others merged to form more substantial objects. Over millions of years, the largest of these protoplanets cleared their orbits of smaller debris, absorbing it and growing even more. The heat generated from these frequent collisions caused the interiors of these growing bodies to heat up and differentiate, forming distinct cores, mantles, and crusts. This differentiation was crucial for the formation of planets with diverse compositions and characteristics. It wasn't just rocky material that was involved in this process. In the colder, outer regions of the protoplanetary disk, beyond what we now call the frost line, ices could also accumulate. This led to the formation of icy planetesimals, which later became the cores of gas giants like Jupiter and Saturn. In these regions, the abundance of icy material allowed for the rapid growth of massive protoplanets, which eventually gathered thick atmospheres of hydrogen and helium from the surrounding disk. The process of planetesimal formation and accretion fundamentally shaped the architecture of our solar system. The planets formed within the plane of the protoplanetary disk, inheriting its flat, rotating structure. As we observe the night sky and see the planets tracing similar paths, we are witnessing the outcome of billions of years of dynamic interactions, collisions, and growth within that ancient, spinning disk of gas and dust. The fourth concept we need to introduce is the ecliptic plane and how the orbits of the planets align closely with it. Imagine if you could draw an imaginary line across the sky, tracing the path the Sun appears to take over the course of a year. This path is what we call the ecliptic plane. Essentially, it's the plane of Earth's orbit around the Sun, and since the planets in our solar system formed from the same flat, rotating protoplanetary disk, their orbits naturally align close to this plane. Now, let's visualize it. Think of the solar system as a giant, flat dinner plate with the Sun sitting right in the middle. The planets orbit around the Sun much like marbles rolling around on the surface of that plate. Because they all originated from the same spinning disk, their paths remain relatively flat and aligned following the ecliptic plane. This alignment is why when you look up at night, the planets seem to follow a predictable line across the sky. It's not a random occurrence but a direct result of the early formation processes of our solar system. Even though each planet has its own unique orbit, these orbits don't stray far from the ecliptic plane. This is why, during planetary conjunctions, planets appear close together in the sky, even if they are millions of kilometers apart. Understanding the ecliptic plane helps us grasp why the planets' orbits are so orderly and aligned, a testament to the early dynamics of our solar system's formation. This intricate dance of celestial bodies, all moving in harmony along this flat plane, showcases the elegant simplicity of nature's laws. When you stargaze and notice the planets' alignment, you're observing the enduring legacy of an orderly process that began billions of years ago, governed by the fundamental forces of physics. The fifth concept we need to discuss involves the exceptions to the general rule, such as Pluto's inclined orbit, and understanding why most planets still follow the same plane despite these anomalies. Pluto, unlike the 8 major planets, has an orbit that is significantly tilted compared to the ecliptic plane. While the major planets have inclinations of less than 7 degrees, Pluto's orbit is inclined by about 17 degrees. This might seem unusual, but it offers an opportunity to delve deeper into the dynamics of our solar system. Pluto's tilted orbit can be attributed to several factors. One key reason is that Pluto resides in an area known as the Kuiper Belt, a region of the solar system beyond Neptune that is populated with numerous small icy bodies. The formation and evolution of objects in the Kuiper Belt were influenced by gravitational interactions with the giant planets, especially Neptune. these interactions could have significantly altered the orbits of bodies like Pluto, increasing their inclination and eccentricity. Additionally, the early solar system was a chaotic place with many planetesimals and protoplanets interacting gravitationally. These interactions could have scattered some objects into more inclined orbits. Despite these anomalies, the majority of the planets remain in the same plane due to the initial conditions of the protoplanetary disk and the conservation of angular momentum. The disk's flat, rotating nature set the stage for the planets to form in a roughly coplanar arrangement. Even as the solar system evolved, this initial alignment was largely preserved. The gravitational forces between the planets helped to stabilize their orbits, maintaining the overall flatness of the system. Think of it like a swirling carousel where the horses stay on a flat, rotating platform, while a few stray figures might move to different levels due to external forces. So when we look at exceptions like Pluto, we see the result of complex gravitational interactions and the dynamic nature of our solar system. These exceptions remind us that while the majority of planetary orbits adhere to the same plane, the universe is full of fascinating variations that enrich our understanding of celestial mechanics. The sixth concept involves exploring external influences, such as the gravitational effects of nearby stars or passing objects, and how these can impact planetary orbits. While the initial formation of the solar system set the stage for the planets to orbit in the same plane, external forces can also play a significant role in shaping these orbits over time. Imagine the solar system as an island in space. Just as ocean currents and winds can affect an island's climate, nearby stars and passing objects can exert gravitational forces that influence the planet's orbits. Nearby stars, especially those within our galactic neighborhood, can have a subtle but measurable impact. As stars move through the Milky Way, they may pass relatively close to our solar system. When this happens, the gravitational pull of these stars can disturb the orbits of comets and other small bodies in the outer regions of the solar system, like the Oort cloud. These disturbances can sometimes send comets plunging toward the inner solar system, potentially impacting planetary orbits through gravitational interactions. Similarly, passing objects such as rogue planets or interstellar objects can also affect the solar system. Although these encounters are rare, the gravitational influence of a passing object can alter the orbits of planets and smaller bodies. For example, the hypothetical planet 9, if it exists, could be an example of a massive object in the outer solar system affecting the orbits of distant Kuiper belt objects through its gravitational pull. Additionally, over long time scales, the gravitational interactions within the solar system itself can cause gradual changes in the orbits of the planets. For instance, the gravitational tugs between Jupiter, Saturn, Uranus, and Neptune can lead to subtle shifts in their orbits. These interactions can sometimes create resonances where the orbital periods of two bodies become synchronized in a way that amplifies their gravitational influence on each other. One real-world example of this is the resonance between Neptune and Pluto. Despite Pluto crossing Neptune's orbit, their 2-3 resonance ensures that they never collide. Another fascinating aspect is the influence of the Milky Way's gravitational field. The solar system is not stationary. It moves through the galaxy, experiencing the gravitational pull from the galaxy's dense central region and its spiral arms. These galactic tides can slowly alter the orbits of objects in the outer solar system, potentially leading to changes in the distribution of comets and other small bodies over millions of years. In summary, while the flat, aligned orbits of the planets are primarily a result of the initial conditions of the protoplanetary disk and the conservation of angular momentum, external influences from nearby stars, passing objects, and even the gravitational forces within our galaxy can impact these orbits. These dynamic interactions remind us that the solar system is part of a much larger, interconnected cosmic environment. Understanding these external influences provides a deeper appreciation of the complex and ever-changing nature of planetary orbits. The seventh concept involves comparing the solar system's planar alignment with other planetary systems discovered by astronomers, highlighting similarities and differences. Imagine a cosmic detective story where astronomers use advanced telescopes and techniques like the transit method and radial velocity to uncover the secrets of distant planetary systems. One striking similarity is that many of these exoplanetary systems also exhibit a form of planar alignment. Just like the planets in our solar system, the exoplanets in these systems often orbit their stars in a flat, disk-like arrangement. This suggests that the processes leading to the formation of planetary systems might be universal. When astronomers observe these exoplanets passing in front of their stars, causing a temporary dimming of the star's light, they are often able to deduce that the planets are orbiting within a relatively narrow plane. This phenomenon, known as a transit, is more likely if the planets' orbits are aligned similarly to those in our solar system, reinforcing the idea that a flat, rotating disk is a common feature in planetary formation. However, there are also fascinating differences that enrich our understanding of planetary systems. For one, some exoplanetary systems feature planets with highly inclined orbits, much more so than what we see in our solar system. Imagine a solar system where some planets orbit almost perpendicular to the primary plane. This inclination can result from a variety of factors, including close encounters with other stars, interactions with massive planets, or the influence of a stellar companion. Such interactions could have tilted the orbits of these planets, creating a more chaotic and less orderly system than our own. Additionally, some exoplanetary systems harbor hot Jupiters, which are gas giants orbiting extremely close to their stars, unlike anything found in our solar system. These hot Jupiters are thought to have migrated inward from their original positions in the outer regions of their systems. This inward migration could disturb the planar alignment, causing the orbits of other planets to become more eccentric or inclined. Another interesting difference lies in the variety of planetary architectures. While our solar system has small, rocky planets close to the Sun and gas giants further out, other systems exhibit different configurations. For example, some have multiple gas giants in close orbits, while others have tightly packed systems of rocky planets. These diverse arrangements suggest that the processes governing planetary system formation and evolution can lead to a wide array of outcomes. By comparing our solar system with these exoplanetary systems, astronomers gain valuable insights into the forces and events that shape planetary orbits. While the commonality of flat, planar alignment speaks to a shared foundation in disk formation, the differences highlight the dynamic and often chaotic nature of planetary evolution. So, when we look up at the night sky and marvel at the orderly dance of our planets, we can appreciate that this alignment is both a testament to the fundamental forces of physics and a piece of a much larger puzzle, revealing the incredible diversity of planetary systems throughout the cosmos. In summary, the planets orbit in the same plane due to a series of fascinating and intricate processes that began over 4.6 billion years ago. The formation of our solar system started with a giant cloud of gas and dust which collapsed under its own gravity to form a rotating protoplanetary disk. Within this disk, particles collided and stuck together, eventually forming planetesimals and then planets. The conservation of angular momentum played a crucial role in maintaining this flat, rotating structure, leading to the alignment of planetary orbits. The ecliptic plane, which is the plane of Earth's orbit around the Sun, showcases this alignment beautifully as the orbits of the planets closely follow this path. While there are exceptions like Pluto's inclined orbit and the influences of nearby stars and passing objects, the overall planar alignment is a testament to the orderly processes of our solar system's formation. Comparing our solar system with other planetary systems reinforces the idea that a flat, rotating disk is a common feature in planetary formation. However, the variations we observe also highlight the dynamic and diverse nature of planetary evolution across the cosmos. The marvel of our solar system's formation, from a spinning cloud of gas and dust to a beautifully aligned array of planets, is a reminder of the incredible forces at play in the universe. We hope this exploration has deepened your appreciation for the celestial mechanics that govern our solar system. If you have any questions or thoughts, please leave them in the comments below. Don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss our upcoming explorations into the wonders of the cosmos. Thank you for watching, and we'll see you next time.